We are. So, are you ready? I can hear you.
Hello?
Yes, we can
Can
hear
you
you.
hear me?
Yes. Okay, our next speaker is Dr. Elham Saremi from IPM. She's going to talk about the monitoring survey of long period variable stars in the local group dwarf galaxies. Okay, thank you.
Thanks. Hello, everybody. Thank you for giving me time. I'm so thankful from organizer for nice conference. I want to talk about dwarf galaxies in the local group and study of star formation history and dust production of them based on a group of stars that name the long period variable stars or LPV stars. For the first time in 1936, Edwin Hubble have named local group for our home. At that time, he only identified a few members, including three main galaxies, Milky Way, Andromeda, and Triangulum, and some of dwarf galaxies such as the Magellanic Clouds, M32, M110, IC10, and IC10 and IC1613 and NGC6822. But now we discover more than 70 galaxies in the local group. Dwarf galaxies are the most abundant type of galaxies in the universe due to their proximity, variety, and a wide range of metallicity. The local group dwarfs offer a unique opportunity to study the connection between stellar populations and galaxy evolution. Despite many studies in recent years, there are still a lot of open questions about them. For example, is gas only removed from dwarfs or can be recreated? Or to what extent and when their star formation was quenched? And so on. With studying about the star formation history of these dwarfs and dust production, we can answer to these questions. One of the best methods for this study is identifying of AGV stars that I will talk about them in following. In the latter stage of evolution, stars with birth masses ranging from 0.8 to 8 solar masses experience a short pulse about 1 to 13 megayear on a region of HR diagram known as asymptotic giant branch or AGB. They have hydrogen and helium concentrating shells around a degenerate carbon-oxygen core. These stars can be carbon type or oxygen type based on metallicity and initial mass. Stars with birth masses of 5 to 10 solar masses become the brighter that named super AGV stars. These stars experience hot bottom burning at the base of the convective envelope. The rest of carbon is burned into nitrogen and oxygen, so these stars remain oxygen-rich. Red supergiant stars are brighter still and come from even more massive progenitors up to 30 solar masses, ending their lives as supernovae. Instabilities between gravitational and radiation pressure at the end of the evolution of these stars cause the long period variable or LPV stars. These stars have radial pulsations in their atmospheric layers with periods of several hundred days. They are the coolest and brightest points on the CMD. The pulsation drives shocks through the circumstellar envelope, dissipating in regions where density and temperature are suitable for dust grain formation. Radiation pressure upon these grains then helps drive a stellar wind. These winds cause AGV stars to lose up to 80% of their masses to the ISM. Some sources have suggested that this share of dust production not only competes with the production of dust through supernovae, but may also outperform them. The low surface temperature of HGB stars cause a radiation in the IR range, so we can observe them less obstruction by dust. Generally, understanding of stellar pulsations and dust production are necessary for studying chemical enrichment of galaxies. LPV stars trace star formation history of galaxies from last 10 gigayear to 10 megayear ago due to a wide range of masses. Because these stars are in the very final stage of their evolution, so they have a maximum of luminosity. So the luminosity of them is more directly related to their birth mass. With identifying LPV stars in nearby galaxies and with helping theoretical stellar evolution models, we can relate magnitude of them to their mass, and then using relative between mass and age and pulsation period, so we can estimate star formation history of galaxy and total mass of it. With these characteristics of LPV stars, our team decided to study the total of dwarf galaxies of local group with a unique method using the LPV stars. For some of dwarfs, such as Magellanic Clouds, NGC 147, NGC 185, and IC 1613, the LPV stars are identified before. So we use them for studying of the star formation histories of these galaxies. For example, the Magellanic Clouds that are irregular dwarfs that can observe them from southern hemisphere of Earth. With using LPV stars, we found a scientific difference in the star formation history of the Magellanic Clouds. For the large Magellanic Clouds, the bulk of the stars formed about 10 gigayear ago, while the strongest episode of star formation in the small Magellanic Cloud occurred a few gigayear later. NGC 147 and NGC 185 are two massive satellites of Andromeda Galaxy that apparently they seem to be companions, but they have different evolution. As you see, two color magnitude diagram of them are here. Green points are the total of HGB stars, and the blue points are long period variable stars, and the red points are carbon stars. We calculated the star formation history of these dwarfs based on LPV stars and stellar evolution models. For NGC 185, we found that the main epoch of star formation occurred in 8.3 gigayear ago, followed by a much lower but relatively constant star formation rate. In the case of NGC 147, the star formation rate peaked only 6.9 gigayear ago, staying intense until 3 gigayear ago, but no star formation has occurred for at least 300 megayear. Despite their similar masses, NGC 147 has more slowly than NGC 185 initially, but more dramatically in more recent times. This is corroborated by the strong tidal distortion of NGC 147 and the presence of gas in the center of NGC 185. And about IC 1613, that is a local group dwarf irregular galaxy at a distance of 750 kiloparsec. The absence of a dominant epoch of star formation over the past 5 gigayear suggests that IC 1613 has evolved its isolation for that long, spurred harassment by other local group galaxies, in particular Andromeda and the Milky Way. For studying other dwarfs of the local group, we have conducted an optical monitoring survey of the majority of dwarfs. That is a complete sample so far with the Isaac Newton telescope at the La Palma. The La Palma is one of Canary Islands. We have used wide field camera that consists of a 4 CCD that covers 34 cross 34 square arc in each monitor. In order to identify the LPV stars, we have decided to monitor over 10 epochs spaced approximately 3 months apart, because LPV stars vary on time scales from about 100 days to 1,300 days. We observed from June 2015 to February 2018. We lost the nights of October 2015 due to the bad weather condition. Excuse me, our selected sample included 43 dwarf asteroidal, 6 dwarf irregular, and 6 dwarf transition, and 4 globular clusters that all of them are visible in the northern hemisphere. Observations are taken in the WFC Sloan I and Harris V filters. We selected I band because the spectral energy distribution of full evolved stars peak around 1 micron, and contrast between the LPV stars and other stars is enhanced. We have also observed in the V band in the extra times for monitoring the variations in temperature and dust radius, and to more accurate SED modeling. We have chosen exposure times that yield sufficient signal to noise. The I-band amplitudes of pulsating LGV star are more than 0.1 magnitude. So for detecting a small change in magnitude at different epochs, we selected signal to noise equal 10 for the faintest star on the RGB. For the processing, we have used telepipeline. The main characteristic of this pipeline is pursuit of astrometry. Here you can see an example of our image that it is processed with tele, that is a 6-B dwarf galaxy. Because having crowded stellar fields, we had to use a point spread function method for photometry. We used the output All-Star Alpha package developed by Peter Stetson. Also, for identifying of LPV stars, among other stars of our catalog, we used one method similar to Welch-Stetson method. Here, I would like to say some of results about our objects, Andromeda I dwarf galaxy, for example. Here you can see the example of light curves for 3 variables candidates of Andromeda I dwarf galaxy and a non-variable star for comparison. The color magnitude diagram of Andromeda I catalog is shown here. The I magnitude are drawn versus V minus I color. The black squares are identified stars, and greens are LPV stars. For removing foreground stars, we have cross-correlated our catalog with the Gaia DR2 data. And isochrones from Marigo et al. 2017 are overplotted. The horizontal dotted lines represent the tip of RGB and tip of AGB stars. The most of AGB stars are between two lines that only some of them are in the end of the AGB phase and are LPV. We estimated the amplitude of variability by assuming a sinusoidal light curve shape. Here is the I-band amplitude of variability versus I-band magnitude, and in the left panel, and versus V minus I color in the right panel. The amplitudes stay below 3 mag and generally less than 1.5 mag. This plot shows while the brightness increases, the amplitude of variability decreases, which is a known fact for populations of LPV stars. Among very dusty AGB stars, start with redder colors, have the largest amplitude. These are often also relatively luminous. Some LPV stars, highlighted by red crosses, are detected only once or twice in the V-band or not at all. Their colors are estimated on the basis of the completeness limit. Their large amplitudes and red colors the large amplitudes and red colors make them prime candidate for being dusty AGB stars. We limited our LPV catalog to those stars with variability amplitudes larger than 0.2 mag in the I-band. We estimated some of physical parameters of galaxies, such as half-light radius and distance of galaxy based on the RGBT. Here is a logarithmic form of the stellar number of density black points as a function of radial distance to the center of Andromeda I dwarf galaxy. Error bars take into account the Poisson uncertainty in the counts. On the right vertical axis, the surface brightness is constructed based on the integrated flux of the identified stars, red points. The blue solid curve represents the best exponential fit to the data. We estimated a half-light radius of 3.2 arcminutes. The tip of the RGB is a discontinuity in the RGB luminosity function, which can be used as a standard candle. The metal-poor RGB stars in their evolutionary path experience a core helium flash and then leave the RGB branch. The absolute volumetric luminosity of this point is varying only very slightly with mass or metallicity, and thus it can be considered to be constant. We obtained the distance models 24.41 mag for Andromeda I dwarf galaxy. This result is in good accordance with other studies. Here you can see an image of Andromeda I dwarf galaxy while it is showing the special location of our identified variable candidates. The half-light radius of galaxy is marked with a magenta ellipse. From 100 identified line period variable stars in this dwarf, 59 are inside into half-light radius. Boyer et al. Used the Spitzer Space Telescope to identify dust-producing AGB and massive stars. They named that project Dustings, means dust in nearby galaxy with Spitzer. Dustings comprise 3.6 and 4.5 micrometer imaging of 50 dwarf galaxies within 1.5 megaparsec in 2 epochs, spaced approximately 6 months apart. They tried to find extremely AGB stars, that is known as XAGB stars. These stars make more than 75% of dust produced by cool-level stars, while they include less than 6% of the total AGB population. We cross-correlated our results with mid-IR data of Spitzer for estimating mass loss and dust production of LPV stars. 75% of detected sources and 98% of LPV stars are detected at mid-infrared wavelengths. We show evidence for the presence of dust-producing AGB stars in this galaxy, including 5 XAGB stars, while dustings found only 3 of them. You can see them with red circles. As you can see, here we have modeled some of their spectral energy distributions to obtain an approximate estimate of the mass return rate of dusty AGB stars. We modeled the SED of 4 dusty LPV stars from optical to the IR using the publicly available dust radiative transfer code dusty based on Ivosican Elixir. These SED are composed of measurements in the eye filter of the INT with magenta points. These stars had no V-band magnitude. And for SDSS filter U, G, R, and Z with black points, 2 mid-IR bands of Spitzer, 3.6 and 4.5 micrometer with red points, and 4 mid-IR bands of Wise with the blue points. The horizontal error bars on the data represent the width of the photometric passbands. Photometric uncertainties are shown with vertical error bars. In the absence of spectroscopic confirmation, we use both types of dust species for matching fits, assuming a grain mixture of 85% amorphous carbon and 50% silicon carbide for a carbon star, as you can see with dotted lines, and astronomical silicates for an oxygen-rich star, that it is shown with solid lines. Different values of optical depths and luminosity were scaled until an acceptable match was obtained on visual inspection. The mass loss rates of these dusty stars are in order 10 to minus 6 solar masses divided year. And this project is continuing. Thank you for your attention.
Okay, thank you very much. It's time for the question. I just wonder if anyone has a question. Let's see. I can't see anyone raising a hand. I have just, maybe I can ask a quick question while waiting for the people. I just wonder